Hello. I have informed Arvind to take over. I have told him. Yeah, I'll tell him. I'll tell him now. I'll tell him now. Good afternoon, everyone. Welcome you all for the afternoon session of this day 3 program. I would now request Mr. Arvind from Speaker to kindly introduce today's speaker and the topic.
Good afternoon. Can you all see my screen?
Yeah, we can see.
Yes.
Good afternoon. A warm greetings from Speaker. On behalf of Speaker, we would like to welcome each one of you to today's session. Our vision at Speaker is to connect academia with the industry by bringing in industry experts to impart their knowledge with the others. Our session for the day will be on basics and application of IoT. This session will be delivered by Mr. Girish Kumar, who is the founder and director of I2 OT Labs, Bangalore. Girish is an industry veteran with 25 years of experience across domain exposure with tech giants like Motorola, Symbian, Nokia, RSA, Cisco, etc. He is also an alumna of Illinois Institute of Technology. Thank you, Mr. Girish, for accepting our invite. The duration of today's session will be 90 minutes, including the Q&A session. We request you all to mute your mics to avoid interferences. You can type in your queries in the chat box and we will answer it during the Q&A session. Once again, we thank you for your time and we believe that the session will be useful to you. Over to Mr. Girish. Mr. Girish?
Okay. Thank you very much, Arvind. Can you hear me?
Yes.
Okay.
Girish, sir, we can hear you, but we cannot. I think your video is off.
One sec. I will. Can you see me now?
Yes.
Okay, perfect. So, good afternoon, folks. So, Arvind has given an introduction about me. So, I'm not going to get into much more about myself. I'm going to straight away start on with the topics on IoT. So, during the course, during the presentation, if you've got any doubts, please put it in the chat box and I will definitely answer to it one by one during the QA session. Let it be any kind of doubt. Don't worry about it, whether it's right or wrong. Please post it. We will address it. Okay? So that's all. So let me start the presentation right now. Can you all see my screen? Can you all see my screen?
No, sir, it's your video.
It's my video. Okay, so let me correct that. Can you see my screen now?
Yes, sir.
Perfect. It's a green screen what you're seeing right now, right?
Yes.
Yeah, sure.
So I've switched off my camera and I will be presenting it through the slides directly. Is that okay? Okay. So, Internet of Things. So what exactly, the question quite often I get is, what exactly is the Internet of Things? This is actually a lot of debated question, lot of students, lot of industry expertise do come and ask me these questions and I ask them back, what is that you have understood? So I keep getting different vague answers. So let me tell you a little bit of background about what exactly this Internet of Things, how it evolved. So the original definition of Internet of Things, IoT, came from McKinsey. So IoT means sensors and actuators embedded in physical objects and are linked through wires and wireless network, often using the same internet protocol that connects the internet. So this is a pretty long definition. It was the original definition came up, but let's see how this big definition came up. So the term Internet of Things is more than 4 decades old. This idea of connecting devices has been there for a long term when the internet was in the experimental stage. So it was originally proposed by a person by name Kevin Ashton sometime in 1999. So Internet IoT, the concept was there, but it was never called as IoT. Only in 1999, a term was given. So Ashton was working in a supply chain company, in a supply chain project, and he wants to attract the senior management's attention on a new technology which he is proposing with the help of RFID. And the internet was one of the trending things during that time, and he termed the term Internet of Things. So that's how it came. So originally, for connecting RFID devices, so he was working in a, I think he was working something to do with supply chain, warehouses and all. So he just wanted to use RFID based device. All of you know what an RFID by now, RFID devices, and he wants to connect it and to track his shipment and all those things. So he came out with this idea called Internet of Things. So, so Kevin himself came out with a definition for this, and he gave a video also about what IoT is, what Internet of Things is. But end of the day, it is nothing but a set of sensors and a set of actuators connected to a computer through the internet. So when you say computer, yes, it can be anything. It can be a laptop, it can be a desktop, it can be a cloud computer, it can be a microcontroller or something like that. You are connecting and integrating it to solve a particular problem. So if I say a computer, you know what a computer is. You know what a camera is. Now, if you want to solve a problem, we need to integrate many things together. And that solution is what is called an IoT. There is nothing called an IoT as a piece. If let's say I'm saying, it's not, it's very difficult to say camera system or a, it's not like that. It's a term, and it's a term used for building solutions, end-to-end solutions with the help of internet. That is what it's all about. So as we progress, I will give use cases. Then at that point of time, you will get a lot more clarity into this particular term called Internet of Things. Now, before we get into Internet of Things, I want to clear some of the doubts here. Some of the key questions which come around with it is the term embedded computers. So what exactly is an embedded computer? So some of you know, but some of you, I know it's not very clear. See, we all have used computers all our lifetime. Of course, some of you are faculty members, some of you are students. So some of you started using computers a few years back, but we all mostly used computers as desktops and laptops. So they are standalone. But when the same computer becomes a part of another larger system, or when the computer itself becomes a component of something else, we call it an embedded computer or an embedded system. A very good example of that is here, the microwave oven, which you have, some of you have it at home, some of you have seen in the restaurants, in bakeries and all, you would have seen this, these microwave ovens which are used for heating food. So this has got a computer inside it. Of course, it's a microcontroller based computer. And here you don't get to see computer. And we don't call this as a computing equipment, but we call this as a microwave oven, but it has got a computer inside. Then that computer is called an embedded computer. Here I have a smart TV. Traditional TVs didn't have a computer. It just had a picture tube and a tuner circuit. That's all. But today, LCD screens or LED screen TVs comes with an inbuilt computer, usually an ARM core processor based computer running Linux inside that. And you have a touch screen, all sort of fancy features come. So you could directly stream YouTube video, browse web and all those things, but you don't get to see the computer. So that is smart TV is another example of an embedded computer. Now you have cameras do have embedded computers. Your car has got an embedded computer. Your flights do have your flight also has got a computer inside that, which completely controls. You would have heard of autopilot. You don't get to see that computer. So all these things consist of an embedded. When the computer becomes a part or a component of a much bigger system, we call it an embedded computer. So is that clear? So we'll go to the next slide. So what's the connection between embedded computers and IoT? We will come to that. Okay, so I just want to introduce what an embedded computer is, and then we will connect all these things together. So what are the applications of IoT? So IoT finds applications in almost every field today. Any internet connected device, we call it under as an IoT. Definitely your home automation, your automobiles, hospitals, space and defense unit, manufacturing units, bank and insurance companies. So out of this, we will see a couple of examples of all these things. Now, just to give you an introduction of the connection between IoT and embedded systems. If you look at this manufacturing plant over here, if there are computers, do you get to see here? Definitely you don't get to see, but there is a computer inside. The same thing with this car. There is an embedded computer inside, and that is connected to an internet, sending some data, and we are solving some problem. Same thing with your flight also. So let's see how all these things put together to form a solution as we progress. So now let's quickly look at our industrial revolution and where it all has started from. Around 1970, the first industrial revolution was the transition of new manufacturing process using water and steam. So way back, the industrial revolution started when we started using steam engines. So in 1840, something called an electrical technology was introduced and to achieve better sophistication. So that was the second wave. The third wave was around 1970 when the electronics stepped in. So the electronics came in, and that is when the concept of automation has really entered. So automated manufacturing machines. Till 1970, everything was manually controlled. Immediately after that, the fourth industrial revolution started with the smart machines and storage system. That is nothing but computers got integrated into manufacturing. And this is what the possibility of IoT, industrial IoT, what we know as. That means the computers got connected to that. The next wave is Industry 5.0, the revolution in which man and machine reconcile and find ways to work together to improve the means. So we are currently in the fourth Industrial Revolution 4.0, where the smart machine storage systems are integrated to achieve better automation without human intervention. So if you look at many of our food processing plants are completely untouched by hand, and they're completely monitored through internet. So that is where the fourth wave comes. And the fifth wave is we are trying to optimize the role of a human being and the machine. So a lot of questions are being asked. If machines are going to control the whole thing with artificial intelligence, IoT, machine learning, what is the role of human beings there? You don't need humans. So what is going to happen to humans? No, that is not going to be the truth. The truth is man and machine reconcile together to find optimal ways of improving the efficiency of production. So we are yet to go there. So right now we are in the fourth stage, and let's look at some of the use cases behind this. Now, I wanted to explain to you a couple of use cases which are there in IoT. So what happens when IoT really comes into use? How does the world looks like? Let's say today we are quite comfortable with Uber, where you want to order a taxi, call it taxi, a cab. We are completely comfortable with Swiggy, Zomato for food. Now, how about for a workshop? So we call it Swiggy, Uber are called aggregators or some service aggregators. So they don't have a hotel with them. Swiggy or Zomato don't have hotels. They don't have any customers. They are just the in-between party who integrates the restaurants with the consumers through an automated platform. So they have very small manpower. With that, they are doing a lot of business. Now, let's say you want to have a workshop today, which is one of the biggest problem with all of us owning an automobile. Everybody can afford an automobile today. You're going out with your family for a trip. Suddenly, your car develops a fault in the middle of highway. What happens then? You're in the middle of nowhere. Traditionally, what people do, people stop the car somewhere, ask the locals, where is the nearest workshop? So you find the nearest workshop, take an auto rickshaw or something like that, go there, call the mechanic, come. It's a long process. But with an IoT enabled car or an IoT aggregated mechanics shop, this is going to change a lot. So let's see how it's going to work. Let's say your car develops a fault. Definitely, the GPS satellites automatically detects where your car is. So your car's location is completely known at that point of time. Definitely, I assume the electrical system is not in fault. Now, you press a button, find mechanic, either through your mobile phone or through the user interface on your dashboard. What the system will do, system will contact the aggregator who is offering equivalent of Swiggy or Zomato for the workshops. Locate the nearest workshop, inform the workshop guy, there is a person like this is stranded in the middle of the road. He's stuck in the middle of the road, needs help. And the number, your mobile number will also be given to the workshop guy. The workshop guy calls you back and he comes to the spot. You don't have to talk to people there, here, run, catch an auto rickshaw. Automatically, the nearest workshop is located and you get to reach the workshop guy comes, offer you the service and he gets. So it helps the consumer as well as the workshop to get more business. So workshop guy don't have to put advertisement boards everywhere. He just have to sit in his workshop. He keeps getting calls based on where the location of the car. And the good part is, let's say you have a Sandro. Definitely you don't want to go to a local workshop who is not authorized. You want to go to a Hyundai workshop. The system can locate just based on your GPS satellites data, your latitude and longitude. System can locate where is the nearest Hyundai authorized service station is. And that service station guy will get this message and that person will come down and repair your car. So this is one of the interesting use cases when IoT steps in as an aggregator for workshops, completely automated. Let's see how IoT can help you in case of an emergency. Let's say your car, I don't want to say your car, let's say one car met with an accident. It's an IoT enabled car. Definitely, the accelerometers fixed inside the car will detect there was a collision and the car is stopped. Definitely, there is a damage and we need to take help. The system does not know the condition of the driver or what happened to the driver. Irrespective of what happened to the driver, it will first use the GPS satellites and locate its latitude, longitude. Through the internet, it will immediately reach out to the 3 emergency service people. The first one is the police station. Second one is the nearest workshop. The third one is the ambulance service. So, as soon as the message reaches these 3 emergency service locations, either through a WhatsApp or whatever communication mechanism, we are still yet to evolve a lot of protocols behind this particular service. It is still in the early stages. What's going to happen is the ambulance service is going to deploy an ambulance. The fire force guy, the workshop guy is going to send a towing truck, and all 3, the police will come to the spot and do the needed rescue mission, remove the car from the road, clear up the road, and the person is shifted to the hospital. So irrespective of the condition of the driver and the passengers, the message will automatically reach the needed people, and emergency services will be deployed. So this will happen automatically. We will see a little bit of sensors. We'll talk about this particular use case a little later based on the availability of time. Now, what is the relationship between embedded computers and IoT? I think by now you would have got an idea how embedded computers and IoT is connected together. In most of the use cases where manufacturing, automobile, medical, or healthcare, all these fields, yes, we need embedded computers, where computers are a part of a larger system, and that is connected through the internet, and that is networked through the internet. So here you can see definitely there will be a server somewhere who get to know the location of the accident and find out the nearest police station, nearest workshop, nearest ambulance service, and inform them. And the ambulance service guy, all three of them will get the exact Google Map location. Then from the Google Map location, they will find the shortest and the easiest, fastest route to reach there. Not the shortest, the fastest route to reach there automatically. Today, what is there is an efficient Google Map, which can help you to navigate. But the other infrastructure is still yet to evolve. It is still under development. It's an informal stage. Many companies are working on it. With the arrival of electric cars, definitely this use case is going to become a lot more popular. And this is going to happen quite often. And you don't have to really look for somebody, the locals, to come and call the police. It will automatically happen through the background. Even if it happens in a lonely area where nobody has seen. That's the advantage of such a system. So how did IoT evolve? So though I talked about Kevin, who coined the term IoT in 1999, about 21 years back, the actual concept of IoT was there way back in 1969, when the first bare bones of internet was under the development. So 1969, when ARPANET was developed for the US defense, the concept of connecting sensors through the internet was already there in the picture. Only thing, it was not implemented because of the technology was in the early stages. By 1991, when the first web page was created by Tim Berners-Lee, and the beginning of TCP/IP, all these things happening. 1984, the domain name system came up. 1989 proposes the World Wide Web. So 1991, the first web page was created. So like that, over time, I didn't put it in the sequential order. Just want to tell you some of the timelines. And eventually by 1999, Kevin Ashton proposed the IoT. And the first commercial product, according to me, I may not be right, what I know is sometime in 2000, LG announced its first internet refrigerator. So I remember LG talking about this particular thing, and it was only just a myth, or I wouldn't say call it a myth, it was just a vision at that time. By 2009, the real Internet of Things was born. By then, we had a lot of reasonably good bandwidth. I would say broadband penetration was there in 2009. In Bangalore itself, if you look, 2005 onwards, broadband became popular, and something like 2 Mbps broadband was available by 2009, and that opened up the research and the work on IoT. So now, obviously, here the curiosity was, what was the first IoT device? One of the first examples of an internet IoT was early in the 1982, when a Coca-Cola machine located in the Carnegie Mellon University, the local programmers could connect by the internet to the refrigerated appliance and check to see if their favorite drink was available or not. So definitely abroad, people was curious. They didn't want to go walk up to the refrigerator and check whether the drink is available. They just want to sit in their workplaces and get to know whether the drink is available or not, specifically the soft drinks. So they developed some kind of early kind of IoT device with a sensor. And this is the beginning point of automated, what we call the cloud computing. So this is another term which is again floating around IoT, which is creating a lot of questions. So a lot of people is not clear about what an IoT, what a cloud is, and how IoT and cloud are related. So today, what we see, the kind of IoT is possible only because of the availability of cloud computing. Otherwise, we would not have progressed this far. So let's have a quick look at cloud computing so that it gives you a fairly good idea. So the problem with the cloud computing, why people don't understand what is a cloud and keep on talking a lot of buzzwords. I keep hearing because a lot of students do come and ask me, a lot of educated professionals comes and ask me, I don't really understand the concept of cloud, keep hearing the cloud. So to get your fundamentals right, the first thing we need to look at it is, what is the problem we are trying to solve here? Why did cloud computing came in the first place? What was the problem it solved? Or what is the motivation behind cloud computing? If you understand what is the motivation, you will definitely be able to understand what cloud is a lot better. So the whole problem started with users needing computers on a lease basis. For example, in my case, I'm an entrepreneur. Even today, I take computers on lease. I don't want to buy a computing resource for a longer time. Invest. It's a capital investment for me. So if I want to buy a server, it will cost me 1.5 lakhs. And I need the server only for a month or two. And what do I do after that? It is just sitting as a dead asset in my office. And this is exactly where an entrepreneur came out with a solution. So here, there are a bunch of people who needs computers on a lease basis. So I don't want to get into the financial accounting aspects. So there are two things, capital cost and the operational cost. So basically they want to cover want to use the computers on the operational cost. Now, this is where an entrepreneur stepped in and tried to solve the problem. What the entrepreneur did was, he bought a room full of laptops and desktops and kept it and connected it with the internet. So anybody can log into these laptops from a remote computer and work on it. And believe me, I have used this service. It was there in our office. Some vendor provided this service for us. So as long as these computers and the laptop what you're using is connected by an internet, you can log into these computers and use it the way you want. And they will charge you for a monthly basis or a daily basis, whatever it is. And that solved the problem to some extent. But there were some unsolved problems in that. One of the first problems they found was the keyboard and the monitor attached to the laptop or the desktop, which is kept in that room, which is leased out, was not being used because people are logging into it from a remote computer. That's a first. Okay, let's solve that problem by removing them. And when you buy a computer, let's not buy keyboard and monitor. Fine, we will solve that problem. But there was something more. Each user who logs in to these computers has got a different requirement. Some of them needs more memory. Some of them needs less memory but more CPU. A third person need lot more of storage and lot more of CPU. But here, when you look at the complete user pattern, you will notice that some users are running very memory intensive programs and they're really running short of RAM. Whereas somebody else who consumes very little RAM. That means two computers sitting next to each other. The user on computer A is really running short of memory. The guy sitting right next to that is having plenty of memory. You're not able to share. So what is actually happening is unused RAM. So what happens, the resource utilization was not actually happening. For somebody might be using high memory, but their CPU usage is very less. So I have come across these situations. Now, this is the problem with isolated machines. When using isolated machines, usage or the resources cannot be optimized as they are distributed across individual boxes. So as long as the resources are blocked inside a standalone computer, you cannot share them. Though people came out with a lot of solutions, hack solutions for that, nothing was commercially deployed. So they tried to solve this problem in a slightly different way. So what was the problem was remove the keyboard and mouse, install an operating system, connect the motherboard to the network through a cable, power up with the UPS. And this is how the Blade server was evolved. So Blade server is a stripped down computer with a modular and designed optimized for minimal use of physical space and power. So this is an example of a Blade server. Blade server is nothing very similar to your desktop. Only thing, it takes minimal space and minimal power. You can, it has got a good internet connection, good Ethernet card, all those kind of things are there. But it can work without a monitor. And so in companies today, a lot of companies have Blade servers. They are very thin models. So problem number one is kind of solved. But the actual problem, what we talked about, resource utilization, is still remaining unused. So how do we solve the resource utilization? Assume all these computers are connected to a central pool of RAM, central pool of CPU, and a central pool of storage. Oh, individual machines, how do we do like that? That is a question. Yes. If we can do this centralized allocation, it is possible to share the resources. Now, how do you do this? The solution came out with something called a hypervisor. Let's see what a hypervisor is. Imagine a computer where you can install multiple operating systems. So take a desktop, what do you have in your institute or in your office, and imagine you're able to install multiple instances of operating system, and those, let's say two instances you're installing, and they are booting up together. Man, how is that possible? Yes, it is possible. It was not possible some 10-15 years back commercially, but today it is possible. You can install two operating systems. They come up. Now, when the two instances of the operating system comes up, these two instances will behave as two separate machines. Multiple machines on the same hardware, that means we need another entity like a scheduler to manage them. That's the problem now. So we have two operating systems running on the same computer. Two of them are sharing the RAMs, sharing the CPU, and sharing the hard disk space. That means we need a scheduler there. So if you talk of Linux or Windows, the latest Windows and all, they're all multitasking or multi-processing operating system. You can run multiple processes or multiple programs in their memory. So that's why you're able to run a Word, Excel, your web browser, many things you can do in your laptop today. Earlier machines, which I have used in my early parts of my career, did not have this facility because they were not multitasking operating system. They can do only one thing at a time. Now, what turned an old operating system into a multitasking or a multi-processing operating system like what we see today is a scheduler. The scheduler schedules the CPU between these multiple programs so that we see them they're running at the same time. In a very similar way, we need a scheduler to schedule the controlled sharing of the CPU between these two instances of the operating system. This software or this entity is called a hypervisor. So we talked about an operating system. Definitely, I'm sure many of you have heard of an operating system. Operating system has got something called a scheduler, and that scheduler is what internally allows you to run multiple programs on your forefront. So right now, when I am doing my presentation, I have got PowerPoint running here. I have got my web browser running here. I have got my Arduino software running. And in my file explorer running, many things are running right now. So how is it possible? Because of a scheduler inside. Now, when the same computer has got multiple operating system coming up, I need another entity called hypervisor and to schedule and manage these individual operating systems. And this is how it looks like. So there are two types of hypervisors. One is you have the hardware. This is called the bare metal type, hardware. First, what you take a bare hardware bought from the shop, a brand new hardware, you first install the hypervisor. Now, after the hypervisor is installed, you go ahead and install your various operating system. You may have Windows, you may have Linux, you may have Mac, God knows what other operating system, or Ubuntu, CentOS, what different flavors of Linux you can install. And they all will run in parallel on top of this. And they all give you a perception that they are separate machines running there. They will have separate IP address, everything separate. So such a system is called a bare metal hypervisor. Now, you don't need to do like that. You on your laptop itself, you have got an operating system. On top of operating system, you can install hypervisor and have multiple operating systems. This is a little not an efficient way. It's only used for academic purpose, but this is what is mostly used in the industry, what we do. And one of the companies who make this hypervisor is VMware. I'm sure you would have heard of this company called VMware. VMware makes this hypervisor. You can buy VMware from them. I think the free evaluation versions also with them. You can download it and you can install it on your laptop, remove all the operating system from your laptop, install a bare metal hypervisor, enable the BIOS, and then you can install multiple operating system and get a feel about how it looks like. So now if you have a bare metal hypervisor, multiple operating system, you have the feel of multiple machines running on the same hardware. When you run multiple instances of the operating system on the same motherboard, it is possible with the hypervisor to provide support to share RAM, CPU, everything. Now the hypervisor not only schedules the execution of different operating systems, it allows you to share the RAM, storage, everything. That means each instance of the operating system is called a virtual machine. So virtual machine means an instance of the operating system running on a blade server like this with a lot of RAM, a lot of storage, and a lot of CPU inside this. So you can have multiple operating systems installed inside this. They will all run and they can share RAM, CPU, storage, etc. because they're running on the same hardware. Now, entrepreneur who was trying to find the solution found this model very practical to be implemented. So what he did was, he went ahead and bought multiple blade servers, installed the hypervisor on it, and installed various flavors of operating Ubuntu, CentOS, Debian, Windows, Mac OS, all those things. And each instance of that operating system started behaving like an independent machine, and those instances were leased out to the end users. Now what happens? One user needs less memory but more CPU. It's possible. Another user needs a lot of storage and less memory and less CPU. It is possible. So whoever needs, they will all get the resource from a central pool. When they release it, it goes back to the pool itself. This facilitated the usage of what you call the resource sharing between the computers which are leased. Now, such an environment where multiple virtual machines run is called a cloud computing environment. And each instance is called a cloud computer. Amazon is one of the vendors or commercial vendors from where you can lease a machine like this. For example, I lease machines. Many of my servers are leased from Amazon. So you can start, you can start, if you want to learn, you can lease a machine from Amazon, a cloud machine with 5 till megabytes of RAM and some 20 gigabytes of hard disk space and one vCPU for about 200 rupees per month. Now, if you want to go for a 1 gigabyte machine and same kind of hard disk space and all those kind of things, you may get it for about $5. $5 means for it's about 450 rupees, about 500 rupees per month, including GST. So there are a lot of companies. Azure is one company giving like that. IBM is giving like this. Then Amazon is giving like this. So many companies are into this space, leasing out virtual computing resources where you really don't have to invest on a hardware and a software. They come with a lot of software packaged inside them. So all these things are possible because of this environment called hypervisor. With the invention of the hypervisor only, all these things possible and cloud computers work. Now, whole concept of can we do IoT without cloud? Cloud is not mandatory for IoT. So IoT can be done with on-prem installations. So where does this cloud, why do we need this? Since some of you, I got a feedback that some of you are new to this world of cloud. I'm just going back and explaining one more point to connect you with the purpose. So if you ask me, yes, I need a computer here. A central computer which is connected to the same internet, which will receive the location of the accident, then maybe the nature of the accident, whatever it is, and then search a database of where the location is, and search a database to find the nearest police station, nearest workshop, and nearest ambulance service. And then the message is being sent to them through some kind of paging mechanism, WhatsApp, Telegram, or whatever it is, through some kind of mechanism it is delivered. So you need a central computer, which is called the server, which will pick up these messages, route it, and deliver it to this. And this central computer can be easily be located in the cloud. That solves a lot of problems. So how does it solve the problem? Computer is in the cloud. What happens is you really don't have to worry about power supply outages. You don't have to worry about maintenance. It's the vendor who provides you with the cloud infrastructure will take care of power, maintenance, everything. He will assure you 24/9 service for that service. In case the hardware crashes, they automatically move your virtual machine from the running hardware to a working hardware automatically without your knowledge. Now, if you want a 24/7 accident service for your car, it's better to have that server hosted in the cloud. Nothing wrong in having a local computer, then that is called an on-prem installation, on-premise. The problem with on-premise, you have to take care, the owner has to take care, or the person who hosts to take care of maintaining that central machine which routes all the messages. So right now, we are having this session through the Google Meet. You can understand the voice packets and the video packets data from my computer is going to a central computer hosted by Google. Yes, there is a hypervisor running there. On top of the hypervisor, a Linux machine is running. In the Linux machine is where the Google Meet server is actually running. From the Google Meet server, the packets, these audio packets and video packets are transmitted to your individual computer. So it's very important, if at all this commercial and a reliability perspective, we use cloud. So for most of the IoT applications, it is preferred to use a cloud server for all the processing part. So as we go more into the case study, I will cover some more details about the relationship between cloud and IoT. Now, we are going to come into a very important topic called sensors and actuators. So, in the beginning, when I started, When I talked about the definition of IoT, I said IoT is all about connecting a bunch of sensors and actuators through internet for solving a specific problem. Now the question comes is, what are these sensors? What are actuators? So let's see what they are. So a typical example before we get into that, we talked about the accident scenario. In the accident scenario, the car collided with something, some other vehicle or some other object with car collided. Definitely there was a shock. How does the embedded computer get to know that there was an accident? The way it is, there is a sensor inside the car called an accelerometer. Typically, most of the shock sensors are built using accelerometer. There are many methods, but one of the known method is using accelerometer. So when the car is running, the accelerometer sends the direction of the car. The car is moving in one particular direction. This is the acceleration and this is the speed at which the car is moving. I will show you an accelerometer a little while. When I show the demo, how we can make use of an accelerometer also, I will show you. It's a part of our demo. So I will show you how it is attached to a motor and how it can be used. So an accelerometer can sense a sudden change in the acceleration when an impact happens. So accelerometer is a good example of a sensor or an impact sensor. So your mobile phones, many of the mobile phones today, smartphones, comes with accelerometers inbuilt. And that's why when you flip the phone, it automatically senses. And similarly, when the phone drops down, some of the phones automatically switches off. It senses an impact and it switches off from further damage. So all these things are sensors. Let's see. Let's take a deeper look at these sensors. A sensor is a device that detects a change in the surroundings and transform it into another form, say an electrical pulse. However, it should not impact the environment and change the process which is causing the temperature or whatever it is. So a sensor can be electronic, mechanical, electrical, or anything. So a sensor means it just translates a change in environment into an electrical pulse. That's a definition. So in the case of our car, the impact was translated into an electrical signal, and that electrical signal was interpreted by an onboard computer, which is a microcontroller, and it's a small computer, detected and translated to the internet. So that's an example. Similarly, there's a temperature sensor which can measure the temperature. So what are the sensors for an IoT? A sensor that can measure the change in environment, transform it in electrical signal. So for example, a temperature sensor can measure the current room temperature and it can give an electrical signal proportionate to the temperature or the temperature to which it is in touch. So any electronic device or a mechanical device can be called as a sensor. So let's take a look at a very simple sensor, which is a thermometer. A thermometer is a temperature sensor. This makes use of the concept of thermal expansion to measure the temperature. So when the thermometer mercury bulb comes in touch with a hot surface, it's begin to expand, and its expansion will be proportional to the temperature. This is one of the earliest sensors man has designed. One of the earliest industrial sensors, I would call, which thermometer is what is being used. But there is one problem with a mercury thermometer. It does not produce an electrical signal as output. Rather, it produces a visual presentation, which you need a human eye or a camera to detect. Now, how do we go about with a sensor which can produce an electrical impulse? Sensors existed much before electronics and computers. Those days, they played a dual role in taking measurement as well as turning that into an action. The simple sensor which we can talk about is a bimetallic strip, which is used in your iron box. You know, the iron box, what we have at home for ironing our dress, that switches off the temperature, switches off the electrical power when it reaches a certain temperature. That happens because there is a bimetallic strip. That strip bends when it reaches a certain temperature and it disconnects. So this is a combination of a sensor come an actuator. So basically let's not worry about actuator for now. Yes, here is a metal, a bimetal strip. Two metals combined together, when heated, it just bends. That means it is able to sense the change in temperature. Even today, many of the IoT sensors are made using this concept. So not only in iron box, in industry also we make use of bimetal strips. So bimetal strip was first invented by John Harrison in the 18th century. He's a clockmaker. So his problem was when it was basically used in the sea because the ship passes through different temperatures, very cold regions, very hot regions. So as a result of that, the clock either used to go fast or go slow. I'm talking about the traditional spring-wound clocks. So the spring-wound clocks used to go fast or slow based on the temperature. So to solve this problem, he designed the bimetal strip. So one of the first applications of bimetal strip was in navigation, and later it was used in electrical industries. Now, is it possible to build a sensor of your own? It is possible. All we need to worry about, a simple sensor can be built with a few meters of copper wire. The electrical variation, the variation of the can be measured. So if you want to make a temperature sensor, really you don't have to use a bimetal strip. Just take a copper wire, wind it few times on some non-conductor porcelain or something like that, and connect it to a circuit like this, using this equation. Change in temperature is when the temperature changes, the resistance increase. So by calibrating temperature against resistance, we can design a beautiful sensor just using a copper wire. So this is one of the sensors what students usually build in the lab, basically for measuring and calibrating temperature. So you can build an electronic thermometer using this concept. Even today, some of the industries where they have to measure high temperature, they use this method. Another method is using a technique called thermocouple, where two metal wires are connected together and one joint. So here is a metal wire A. Usually a copper and iron wire is connected. One end is hot, is kept in a heated source, other one in a cold source. Automatically an electric current is generated here. So this is another kind of sensor which is called the thermocouple based sensor. So today, with the corona, the COVID, many of the non-contact based thermometers use some technology like this. We call it infrared and many other things, but some of them are thermocouple based. So the thermocouple is a lot cheaper than the traditional one. It can measure a wide range of temperature. It has got high response. Since it is not coming into contact, it does not have the heating problem. So there are many pros and cons with the thermocouple based technology. Since you really, the good part is you can measure the distance. You can measure the temperature from a distance. So there were some kind of thermometers earlier which was designed to measure the temperature of the tip of a heated source, maybe an agarbatti or a cigarette which is burning. You just show it over there and can measure it. So that was all based on thermocouple. It's a very, very sensitive device if you use the proper one. Another one is semiconductor-based sensors, which make use of a diode, and it is being biased and then you measure it. This is another method. And the easiest one, if you want to build a small IoT of your own in your lab, irrespective of your background, you can do it. all you need to do is just go and buy a temperature sensor called DHT11. It costs about 100 rupees. It's a very basic digital temperature sensor, temperature and humidity sensor. It uses something called like capacitive technology. Every 2 seconds, it keeps giving you data. So I use this. I will show you a demo of this particular device when we come to the demo phase. I will show you how it is connected and all. So this is one of the easy to use temperature sensors that are available. So I know people from mechanical engineering, people from electronics, electrical, many backgrounds are present in this conference, in this webinar. Any of you are interested in building a simple IoT device, you want to start learning from it, I would strongly recommend start building a small temperature and a humidity sensor. It's very easy. Using a DHT11 sensor, you can build it easily available in the market also. So how do we build it? All we need is a small microcontroller. This can either be a microcontroller called ESP32 or Arduino, or even your laptop will be good enough. Laptop, you need an interface to connect it. It's not directly possible, but definitely if you've got a small microcontroller like this, this is also available easily in the market today. You can just go buy DHT11, connect it with 3 cables to the corresponding pins, write a simple software which runs here, power it up using a mobile charger, it will start measuring the temperature and humidity and it will display to you. Of course, you need a display also for this. So you connect it like this, and this is a software for that. It's a C program which runs and collect the data, and it keeps on printing the data for you. So when it reaches the demo phase, I will show you a quick example of this. In few minutes, I will show you this. The other one is the infrared thermometer that is very commonly available nowadays with the COVID coming into the picture. That is another kind of method that is also used in IoT. So practically, any sensor can be used for IoT application, provided the sensor can give a digital output. So that is the summary of that. In case sensor provides only analog output, we need to provide a digital. We need to provide a analog to digital converter to that and to read it. What are the sensors that cannot be connected to IoT? Well, those who are from the mechanical engineering background in this seminar will definitely be able to appreciate this. This is a Watts governor. Watts governor was originally designed to control the speed of a train, the steam engines. James Watt designed the steam engines, and he used this method. So this is connected to the wheels of the train, and as it goes up, these fly balls will go up. It pulls the lever up and throttle the valve. So as the speed increases, what happens? It pushes the valve and closes the steam. As it comes down, the speed comes down, the valve opens, more steam comes in, and the speed is governed. So this is actually a Watts governor. This is a sensor which is used to measure the speed of the water or liquid, optical sensors, magnetic sensors, vibration sensors, gyroscopes, touch sensors, weight sensors, RPM sensors, GPS, heartbeat sensors. You've got a whole lot of sensors available today in the market. In the last 2 to 3 years, these became so easily and affordable. And this is which triggered the IoT market. Now let's see what are actuators. So we talked about, when we started the discussion, I talked about IoT is nothing but a set of sensors and actuators connected through internet to solve a particular problem. An actuator is a component of a machine that is responsible for moving and controlling a mechanism in the system, simply by opening a valve. So, Pavlov's known solenoid valves. Solenoid valves are nothing but electrically operated water taps. That's a good example of a solenoid valve. So, in your water purifier at home, or in your college, or in your office, you just go near the water purifier. we have got a lot of RO purifier, ultraviolet purifier. You just switch on, the water starts coming up. Switch off, the water stops. How does this work? There is a small electromagnet, small magnet get charged when you switch on, that opens the tap. When you switch it off, the magnet power is lost, the valve is automatically closed. So when you switch on, the water taps is on. Switch off, the water tap closes. Such a mechanism of converting an electrical signal into a mechanical action is called an actuator. So there are a lot of examples of actuators you can see. A simple motor converts an electrical pulse or something like that into a rotation. Similarly, a solenoid valve which switches on a water tap is an example of an actuator. You might have seen this electronic locks for the doors, where you number locks, where you punch in a number, it opens the door, and punches in, it closes the door. That also uses an actuator. So in IoT, for control purpose, we need actuators. So it gets electrical power from somewhere, a control signal from a computer, and translates into a mechanical action. That is exactly what an actuator does. Now, how does an actuator works? Now let's put all these things together. I have a small microcontroller board with me here. Okay. Just if you are from other background, mechanical engineering background or civil engineering background, consider this as a black box for you. Don't worry about it. Those who are from electrical and electronics background may understand what a microcontroller is, what it's a small computer. Now what we do is we connect a small chip called L293D. This is called a motor driver, and then, a relay driver. Now what we do is, if at all I want to switch on this electric motor, so this is a water pump, I connected this particular switch. Now, if I want to switch on this motor, what I do is I will send an electrical signal from my microcontroller to charge this coil, to allow electric current to move through this coil. What happens? This sender piece, the core, will become a magnet, and that will attract this downwards. When it attracts downwards, this circuit is completed. Just a minute. This circuit complete, the motor gets the power and the motor starts moving. The moment when the computer, this particular computer, releases the voltage, this will lose its magnetic power and automatically switches on. So this is a typical example of an automated water pump where the computer controls this particular motor here. Now, instead of this motor, you put a small miniature pump which is used in your water purifier. It gives you purified water. If you go and put the same thing in a farm, a bigger pump, it starts pumping water into it. So actuator, in this particular case, this relay is an actuator. This is the driving IC and this is the computer. So this relay commercially looks like this. So those who want to build a simple computer like this, a simple motor control, you can just buy these things and connect it like this, and definitely it will work. And there are enough and more sample circuits available in the internet using this particular board, ESP32F, you can note it down, or using Arduino, you can build the solution. Hardly you may take about only 2 hours to build something like this. If you are familiar, otherwise it may take about half a day if you are not, if you're a beginner. You can definitely automate a process like this. And here is the source code for that. The way you do it, you just control one of the pins, the relay pin, using up or high or low. This motor can be made to run. So we've got only 13 minutes left. I just wanted to move. So how do we make, my next question is, how do we make this into an IoT device? I didn't talk about that. That is the most important thing coming into the picture. Now, assume this is the setup you have done in your farmhouse, in a farm. Assume you are an IoT engineer. You are building an IoT solution for a farmer. And what the farmer wants, he or she wants to switch on the water pump from his mobile phone. So on the mobile phone, you just go switch on an app, start an app. When you press start, the motor should start pumping the water here. When you say off, the motor should switch it off. So how do you do this? What you can do is this particular board, this particular computer, as long as it is connected to the internet, it can receive a signal from outside and activate this particular line. So remember, look at this code. In this code, what is actually happening is when I make the digital write high and low, when it high, it starts pumping. When it is low, it does not pump. So based on my command from the app, it is made to go high or made to go low. That's the way it works. So as long as I can communicate with this particular board from my phone, it is possible. How do I do? That is done through the public internet. So how does it go right now? Let's go a little more deeper into it. So what we do is, we have the phone here, we put the same ESP32 board, we put the relay and connect this to the motor. Now, ESP32 has got an inbuilt Wi-Fi running on it. So, it can definitely communicate with your phone, and through the Wi-Fi, you can see it running. So you can switch it on and switch it off. And that's how it works. So how do? We run a web server on ESP32 board, access the web server from home through your laptop or mobile. Web server has got direct access to GPIO port. Now using the web, you can control the pump set. So in a minute, I will show you the actual working of this system, how I have built it, and I will show you the components of this. Just bear with me for a minute. Let me switch the camera on. Yes. I'm just going to stop the presentation to switch into the camera mode for a minute. Just I want to show you the setup. Just a minute. And so just I need a little bit of help from you. Can you see my face properly? Or are you seeing the complete screen? I just wanted to show you the complete.
Only face is visible.
Only face is visible, right? Okay.
Yeah.
Okay, now I'm going to show you my setup. So this is the setup I have. So this is the Can you see a red LED glowing there? This is the ESP32F microcontroller board. These are some of the sensors, and these are the motors. Okay, so this is the setup I have. Let me zoom it a little more so that you can see it clearly. Can you all see this right now?
Yeah.
Okay. So I have kept one motor here and the ESP32 controller. Now I will show you how the interface is going to work, how I'm going to control it remotely through a web interface. Just bear with me for a minute. Now I'm going to, can you see a page called Greenwood Farms page right now? A login name and password. Can you see it?
Yeah.
Okay, so this is so you can see this is the IP address of the microcontroller, which I have connected the motor and other device to. I'm going to log into it. I can access this page from my mobile phone also, but since for the presentation purpose, I am showing it from the laptop. So here I have got, yeah, can you see the main menu now?
Yes, sir, it is visible.
Perfect. Yes, could you repeat? What is the question? Okay, so I'm going to start the motor. Now, when you start the motor, you can hear the sound. Let me see it. So I will show you once again. You can hear the sound. Now, here is a dashboard which shows you a lot of data. It shows the status of the motor is stopped, temperature, humidity, etc. So I will come to this temperature and humidity in a minute. Just I want to show you how the motor is worked. So when I'm going to start the motor, start. Motor is running. So the motor is in a stop state. Now, in addition to this, I have a temperature sensor also connected to this. So I will come to that in a minute. I just want to show you how this is being automated, and we'll come back to our presentation. So the way this works is we have the relay, onboard computer, and the pump set. So here I don't have a pump set. Actually, I'm only using a simple motor because I can't, for safety purpose, I can't play with high voltage here. This is connected to a Wi-Fi network. Here, my phone is connected to home network. Through the public internet, it gets connected and the whole thing happens. So from the phone, I send a signal, it travels through the internet, reaches my onboard computer. Onboard computer will switch on the relay and start the motor. So this is how the whole thing works. Now, here the biggest challenge is I need to make sure that through my mobile phone, this smooth form of communication happens here. In this particular demo, all of them are on the same network, but it is possible for me to connect to the public internet provided I have all the configurations installed there to do a little more configuration work over there. So this is how the whole use case works. Now, I'm going to show you in another, we have got another some 15 minutes left. In that 15 minutes, I'm going to show you the next one. The dilemma, the complete end-to-end use case about what we talked about in the application of a farm, a modern day farming problem. How do we solve this? So this is a photograph of a farm. So farmers are becoming more and more knowledgeable and talented. They understand the science of agriculture, and many people are getting into farming nowadays. So you all would have seen around Bangalore, a lot of knowledgeable people are getting into farming. So a modern day farmer is an entrepreneur who is getting into farming. For him, farming is just another source of income. So traditionally, farmers, they have only one source of income, that's their farm. That means farming is just one of their source of income. They have to manage multiple farms at different locations. They have to do different businesses at the same time. Human labor is a problem. Need to track changes in the farms, changing weather patterns, non-availability of water. So there are many problems. So if at all a farmer has to solve all these problems single-handedly with very less manpower, the only option is to go for more and more automation. So if you look at the priority in a farm, it starts with pumping the water. So definitely, pumping the water is a basic need, and our solution will not be much of help to the farmer. The reason is, just by switching on a pump and a remote pump won't help a farmer, because is the pump actually pumping water? The questions happen. The farmer is far away from the farm. So is the water really reaching the farms? Is there enough water in the storage? So remotely sitting, you can't just monitor. You can switch on a pump, definitely the solution what I just demonstrated will work, but it will not solve all the problems in the farm. So how do we do that? So first thing, when the motor is switched on, what we need is to know whether the water is flowing or not. We need a sensor for that. And that is this kind of sensor called a flow meter. This flow meter, what it does is, when the water flows in one direction, it rotates a small wheel, and the wheel has got a magnet over here. And this magnetic rotation is being sensed by something called a Hall effect sensor. Hall effect sensor is a semiconductor device which is kept on near the sensor. This is how it actually looks like. So hardly this, almost you can hold it in your hand. This is how when it is opened. I have the sensor with me. This photograph is from my workshop. I've taken it. So each time when the magnet passes, it sends a pulse. So the number of pulses this sensor gets is proportional to the amount of water flowing. So if the board, what I've just now showed, can be connected to this sensor, from my mobile phone, I will get to see whether actually pumping of water is happening or not. If the pumping is water, how much water is it pumping? So the moment when I switch on the pump, I will get to see how much is the amount of water, the rate of flow of water can be monitored using this particular sensor. That solves one problem. So this is the same sensor which is built using brass, which is for a little more heavier use. So I'm sure those who are from mechanical engineering side would have seen these kind of flow meters very much in your lab. You'll be using a lot for your fluid mechanics, hydraulics, and those kind of purposes. Something very similar which is commercially available can be used in farms today. They can easily be integrated with Arduino or ESP32. There are a lot of interfaces, and enough documentation is available for that. So I'm not getting too much into the code. That solves only one problem. Another problem the farmers faces: when should I pump the water? Okay, if I keep pumping water morning and evening, will that be enough? That is not a scientific way of pumping water. So I can just get an instantaneous data about amount of water pumped, whether the motor is switched on or not. All those things I can do. But actually, I should be pumping water based on the temperature and humidity of the farm. I should know the temperature and humidity in my farm. What is the mean temperature in the last 10 days? Is the humidity dropping? If the humidity is dropping, I need to pump more water. What is the pattern of the rainfall in the last 10 days? Is the soil retaining moisture? What is the soil moisture? I need to know all these things. Then only I should be pumping adequate enough of water. Otherwise, I'll be overhydrating the farms. So I also need access to my historic data in all these things. That means, what was the pattern of rainfall in the last 10 days? Should I, if there was enough rainfall, I don't have to pump really water. Okay, there was no rainfall in the last 5 days. Okay, I need to pump water for 1 hour or 2 hours. How much water should I pump? I should pump enough water such that the soil moisture reaches a certain level. So I need to know my soil moisture. So there are so many questions we need to ask him. So for that, we need to have sensors installed in the farms. We need to install temperature and humidity sensor. We need to install a rain sensor. We need to install a soil moisture sensor. And also, we need to install a wind speed sensor, because wind also plays a role. And also, we may have to install a pH sensor in the farm. So all these sensors, once it is installed, they get connected to this particular computer. Through the internet, you get to know what is actually happening in your farm through this mechanism. So that means we need something more called a database. It's not the instantaneous data. I need the data of the last 1 month or throughout the season need to be collected, archived and kept, and I need to study the data. Based on that is when I should see how much water I need to pump. Because each plant needs different amounts of water at different parts of its growth. During the sowing the seeds, it needs some amount of water. When it is growing, it needs a different amount of water. And the amount of water it needs also depend upon the soil moisture and the humidity, all these parts. This is where IoT databases comes into the picture. So basically, what we do is, we using a sensor, exactly DHT11 I just talked about, will be used for that purpose. You can install DHT11 and a microcontroller in the farm, collect the humidity throughout the day, humidity and air temperature, and a graph will be presented. So using this graph, a farmer can get to know what is the actual environment in the farm. Is it too hot or is it too humid or whatever it is? How was in the past few days? Based on that, they can take a decision to start the pump or not. This is a graph, it shows the different level of soil moisture, the water consumption and the soil moisture. So the sensor at different depth, you insert the soil moisture sensor. Against the rainfall, it shows the water consumption and other factors. So we keep on collecting data from the farm throughout the day about the humidity, air temperature, soil moisture, and it will be presented to the farmer in a very presentable way. Now, remember, a farmer is an entrepreneur. He doesn't have the time and energy to understand these kind of graphs. A person with agricultural BSc or something like that will be interested in seeing these kind of graphs, not a farmer. So that means it has to be presented in a very unique way. This is exactly where the design thinking comes into the picture. Imagine you presenting the soil moisture data using something like this. So this shows at different levels of the soil, how is the water penetration. So this is a scale which shows the depth. This shows the plant, and this shows the hydration level at different levels of the soil. All you need is a sensor like this installed in the farm. So we need all these things together, and this is how leads up to an IoT platform. An IoT platform, what does it collects data from the sensors, store it in the database, and present it to the user in a very acceptable format. This is the level 1 of an IoT system. So using the help of sensors, it keeps collecting data, store it in a database and present it. The next level is you analyze that information and the analytical data is also presented. Then the third is you optimize your operations based on the data which is being collected. So you have the matrices, you analyze the data, collect data, store data, analyze data, and save it in the matrices. And that is being used to optimize. This optimization data will tell you how often you need to start the motor, how often you need to irrigate the land. Depending upon the humidity, wind speed, and temperature, you will be able to decide whether how much long I need to pump. Is the pumping good enough? Has the soil been hydrated or not? These are the three levels of using IoT platform. So IoT platform, what it does is collect data from the sensors, store data, analyze data, and present the information to the end user in a very presentable format. So I just want to give you a quick view about how it will be used in a farm because I haven't shown you that particular slide. Can you see this particular slide? A farm kind of see, can you see this? Can you please unmute and confirm?
Yes, sir, it is visible.
Yeah, very good. So now, a view like this will be presented to the farmer. Now, the farmer has assumed these are his 4 farming areas. You just move your slide, you move your cursor. It tells this particular region, humidity is 50%, temperature is 32 degrees Celsius, and soil moisture is about 45%. He comes over here, it says the soil moisture is less, humidity and temperature is more or less the same. Here, the soil is overhydrated. Humidity is also high. Humidity is relatively low, but soil moisture is okay. So just moving the cursor across the view of the farms, the farmer get to see what is actually happening in the farm. It is not through the graphs and curves. So we need a tool to present, to collect the data and present that in a form which a farmer can easily understand without spending much of time. This is actually what an IoT platform does. It not only gives you instantaneous data, it compares with the old data and also show you what is happening in the farm in this way. I'll show you another way of presenting. Just give me. This is another way of presenting. But one more presentation. Let me see if it works or not. Yeah, this is it shows how the soil. Can you see at the bottom right corner of the screen? As I hover from one farm to another, it is showing different layers of hydration at different levels. So as a farmer is concerned, if it is presented to this farm, it will be very useful and it will be very easy to use. So this farm, reasonably it is hydrated at the top level, but not at the bottom level. Here it is overhydrated, it's all the way going down. Here it is kind of okay. The bottom level is little dry, but the plant is getting enough water. So this is another way of presenting the data. So collect all the data and present it to the useful way to the farmer is the most important thing. Now, let me put all these things together in the demo and show you. Now, I didn't do all those things integrated for your learning, just for the demonstration purpose. If I come over here, you can see what is the status of my motor. It is stopped. What is the temperature, current temperature in the farm? Humidity, soil moisture. What is the status of a rainfall? Because I've got something called a rain sensor. I will show you how the rain sensor works in a minute. The wind speed. And this shows my flow of rate in case the motor is started. So I don't have the flow sensor integrated right now. Now for a minute, I will just sprinkle some water and I will show you how the rain sensor works. Give me a minute. We are almost running out of time. You can just see when the rain comes. The sensor works, it will show you. Correctly, it will show it is working. The rain will become true. For some reason, my wiring is having a problem. Otherwise, the rain will also become true because I have the rain sensor installed here. But now this is how this whole thing is presented. Here, if you look at the temperature, these two data is actually coming from my DHT11, the sensor what I showed you. And this is how the whole code look like. So I have coded it using Arduino front end and ESP32F IC, the microcontroller. And here, this is where I read the temperature and humidity. And you can see it here. The sensor is having a bit of problem because I shook the board. Otherwise, you can see temperature and humidity it is reading. It is showing in the logs. And from here, it goes into a database. And that is from there, it comes onto our screen like this. So for this particular demo, I just put together everything on a small board and I connected using my home Wi-Fi. But otherwise, the same setup can be made to work through the internet also. So that's how this whole setup works. In a few minutes, I will show you a quick slide about the different technologies used in IoT. And then we will conclude the seminar, after which I will open up for discussions and questions. Just give me a minute. So these are called the communication technologies. We have a sensor and an actuator connected to a microcontroller. You have a cloud computer where the database is running and collecting all the data. And the user is sitting in his home through his laptop or mobile phone accessing it. Definitely, all these things has to be connected together by some means. So what are the technologies available today for that? So we have three methods of connecting today. One is using Wi-Fi, which is only a few meters in range. Then you have got something called a LoRa, long range access. It's a narrowband IoT. And then you have the 4G and 5G. These are the three things which can be used for connecting your IoT device to the internet. Once it is connected to the internet, they can communicate with each other without any problem. So Wi-Fi, it operates in 2.4 to 5 gigahertz range. It has got a high bandwidth and the range is of the order of few meters, but ideally it is used for web browsing, streaming and email. And it consumes a lot of power. Yes, it can be used for IoT, provided the IoT device at your home where power is not a problem. But wherever there's a power consumption, where you need a battery backup and all of the things, Wi-Fi is not a really recommended option, especially in a farm. That is when we go for LoRa. LoRa operates at a frequencies much lower. So if you look at Wi-Fi, it operates at 2.4 gigahertz. So if you look at your home Wi-Fi or your hotspots from your mobile phone, they mostly operate at 2.4 gigahertz. LoRa operates at around 500 kilohertz or few megahertz. That's it. Because of the low frequency, you can operate it at a very low power. Even a small AA size batteries can withstand for a longer time with LoRa. So for this farm kind of application, we are only sending few bytes of data. Switch on the motor, switch off the motor, just the temperature, humidity, and other kind of things transmitted every 5 minutes to the central database. All these kind of things, we don't need high bandwidth, very narrow bandwidth is enough. So LoRa will be good enough, and that will be a good method. It can work on batteries also. You don't have the problem of power in the farm. You can just once in a while go and change the batteries or connect to a small solar cell. Now this is also good for, in the animal where the milk, where the farmhouses where you have the cows and other animals are there. You can use it for monitoring their movements and other kind of things. You can't carry a huge power with the cow. So you can put a small LoRa device with a button cell, it will operate. Other one is a common thing what we all hearing, 4G and 5G technologies. The good part about 4G and 5G technologies, the range is unlimited, somebody is providing you the coverage. LoRa, the range is about few kilometers, maybe 1, 2, 3, max 10 kilometers. Whereas 4G, 5G, you can switch on a farm, maybe somewhere in Maharashtra by sitting in Bangalore. That's a beauty. You can, if I have my IoT, my device is connected through 5G or something like that. So the frequency bands are like 700 megahertz to 2.7 megahertz, and it depends on the use. And I don't have to tell you what is 4G. All of us use 4G for our day-to-day use today. And LoRa is an evolving technology, and narrowband technology, and Wi-Fi, I'm sure all of you know. These are the three commonly available methods. In addition, there are some other technologies also for connecting devices to the internet. With all these things, it is possible to connect multiple sensors and actuators to a small computer, microcontroller-based computer, which is in way connected to a cloud, and you can monitor and control what's happening. So in the same way, like we monitored and controlled a farm, operations in a farm, it is possible to monitor a patient. It is possible to monitor the performance of an automobile. We'll get to know the status of an automobile. It's possible to control a manufacturing plant. It does not matter what you're at. Just using a set of sensors and actuators, a small onboard computer and an internet connection, you can monitor and control many of the modern day technology from a remote location. So that is all about IoT. So IoT is all about automation, mostly about automation. Other purpose also it is used. For example, in insurance companies use IoT in different way. They put an accelerometer on your laptop, on your car, and keep sensing the speed and your braking pattern against each location in the road. Then the insurance companies will analyze the data and conclude how safe, how good you as a driver. Based on your driving pattern, they fix an insurance premium for you. If you are a safe driver, your premium will go down. If you are a risky driver, you are doing rash driving, your insurance premium will go up. So based on your driving pattern, insurance companies can fix your premium. Similarly, health insurance companies get to know how physically active you are. Are you a person who is doing exercise or not? So if you're a person who is regularly exercising, your health insurance premium will go down. Otherwise, your health insurance premium will stay high. So IoT data is used in many, many ways, not just for industrial and automobile and farming. Many people use it. It's up to your imagination on how to use it. So with that, I conclude my presentation. Now I'm opening it up to the audience to ask me to ask questions now. I will take your questions. So I overshoot it by 10 minutes. I'm sorry about that. It's a little long topic. I have to cut it short, but feel free to ask your questions.
Thank you, sir. Thank you for that nice presentation. So I request participants, if you have any questions, I request you to kindly unmute and you can directly interact with the speaker.
What is the objective, job perspective, a mechanical student do project in IoT? Okay, so can you repeat that question? What is the job opportunity for a mechanical engineering student, right? Did I get it right?
Yeah, that's right.
Okay. So a mechanical engineering student doing an IoT project is a very good question. So traditionally, if a mechanical engineering student gets a job, you assume it is in the area of machines, design of machines, maintenance of machines, manufacture of machines, etc. Today, machines are all getting automated. They are not manually controlled. So a mechanical engineering student, it's mandatory to know to know about an IoT. At least a simple IoT project will get you know how an electronics part is integrated with the machines. So definitely a companies which are looking for industry 4.0 kind of machines definitely will prefer a candidate with IoT knowledge than with a non-IoT knowledge. So that is one part. Second part is during the career, it will be very easy for a person who has done some project on IoT to pick up the concept of the latest machines. Because today, almost all machines are interconnected through the internet. So you know, understand what happens. So your training becomes a lot more easier if you are joining an institute, joining a company with prior knowledge of IoT.
Thank you, sir. There is one more question that is from YouTube. We are just taking it up.
Sure.
Question from Sharmista. They're asking, what are the existing LoRa devices which can be used for applications?
LoRa devices can be okay. So LoRa is actually a communication technology. So let's say you want to have a device, a small microcontroller device is connected to LoRa. You can buy the LoRa hardware and it can be connected to your device through USB or one of the standard interfaces. So a lot of companies making LoRa devices today, if at all you want to integrate, that is basically the LoRa hardware means the communication hardware. Just to give an analogy with the Wi-Fi, some of your laptops come with a Wi-Fi dongle where you need to plug in the Wi-Fi dongle to your laptop, your desktop to get Wi-Fi access. Very similarly, the LoRa dongles for is available in the market. So you can buy that LoRa dongle and connect it. It's coming from 2-3 companies makes it. I think Adafruit makes it and ThinkSpeak also make it. You can buy it from them and integrate it. These are the 2 companies which make LoRa hardware that can be connected to most of the existing boards. Now, are there any ready-made IoT devices which are available in the market which has got LoRa complaint? I really do not know. I have seen it in many of the exhibitions, companies demonstrating LoRa-based product. For example, LoRa-based water meters are there. LoRa-based power meters are there. Energy meters are there. Yes, there's a company called ThinkSpeak. I think they have made these LoRa-based IoT devices. I have seen them in their demonstrations.
Thank you, sir. Any other
Right.
questions? Any other queries from participants? Let's see. Okay, so if there are no further questions, can we conclude this session? Mr. Arvind, you are there? Hello?
Yeah, hello.
Yeah, can we conclude this session?
Sure. If there are no questions, then we can conclude.
Okay. So, yeah. So, Girish sir, it was a very nice presentation. Not just overview of IoT devices, but you have also demonstrated how these devices can be applied in real-time applications. So that is something which is very much appreciated, I believe, by all the participants. I'm sure that they have learned a lot of new interesting topics from this particular session. So I would request the participants that, if you have any further queries, please get back to us, write back to us. We'll try to reach out to the resource person, and we'll revert back with the answers for your questions. So with that, someone is asking, can you please share the contact details of the speaker? I'm sure we will be able to do that. I think SpeakEd probably you can directly get in touch with them, or we will try to uh, get you through the contact details of the speaker. So thank you very much, sir, Girish sir, for that
You're welcome.
excellent presentation. And on behalf of all the participants as well as NMIT, my heartfelt thanks to you. Thanks for accepting our invitation and presenting an excellent session.
So thank you very much, folks. Have a nice evening. Bye-bye.
Yeah. So I request participants to kindly give us the feedback of this particular session. The feedback link has been posted in the chat box. Kindly ask. So with that, I would like to conclude this afternoon session. So thank you one and all.
Bye-bye.
Thank you.